So 1.15, this is very much related to the last section that we talked about. So it'll be a little bit more practice. It's going to talk about linear and exponential change. So linear change, the first thing you see in there is line. And all linear change is, it's just like our arithmetic sequence. So linear is the same thing as just an arithmetic sequence. And exponential change is just the same thing as our geometric sequence. Okay? So we're just going to look at it in a slightly different way, but it's the exact same thing. Okay, so let's look at A. So if it says, suppose Twitter's number of tweets in billions per month over a 6-month period in July went from 8 to 8.4 to 8.82 and so on. So what I want to do is I'm going to fill in these charts, and I'm going to find if they're an arithmetic or geometric sequence. And after I find those, I'm going to make my nth term for both of these. Okay. So let's just fill in our term numbers and our active users and our number of tweets first. So let's start with A. So I'm going to start with term number 1, and I'm going to go 2, 3, 4, 5, and 6, right? So that just represents the 6 months that we're looking at for Twitter's numbers, okay? So how many tweets did I have in the first month?
8 billion.
Right, 8 billion, right? How many did I have in the second month?
8.4.
Right, 8.4. So what I'm doing is just going down this row and just filling in this column with it, right? So the next one would be 8.82, then 9.26, 9.72, and finally 10.21, right? And that's in billions, right? Okay, so that's in billions. So am I changing in the arithmetic sequence way, or am I changing in a geometric sequence way? So how am I changing here? Well, isn't arithmetic, am I adding the same number every time?
Right.
So if I go from 8 to 8.4, we're adding 0.4. How do I get from 8.4 to 8.82? Am I adding 0.4 again?
No.
No, I'm not, right? So what do I have to multiply by from 8 to 8.4? So right, so we know it's not an arithmetic sequence, so it's probably a geometric sequence then. So what do I have to multiply 8 by to get to 8.4? Well, is there any easy way that I can find that? So I just have 8 multiplied by some number, so I'm just going to put a question mark, and that's going to equal 8.4, right? So maybe what I can do is, what if I just divide 8.4 by 8, and that'll just be like what I'm changing. So it's kind of like the percent increase that we've talked about, right? So let's do 8.4 divided by 8. And if we do that, we're going to get some number, and that's just going to tell me how much I'm changing by. So it's just like your finest minor initial over initial. So we're just looking at what we're changing by. So 8.4 divided by 8, we get 1.05. So what that's saying as a multiplier is all we're doing is we're just increasing by 5% from 8 to 8.4, right? So what if I do that multiplier, 1.05, and multiply that 8.4 by 1.05? If we do that, we should get the next term in the sequence. So if I do 1.05 multiplied by 8.4, I'm getting 8.82, right? So we can keep doing that on and on. But what I see is this is what I'm changing by each time. The 1.05 is what I'm changing by each time. So I can say that that 1.05 is my B. That's just my multiplier, right? That's just what I'm changing by each time. And then my first term is just 8. So my first term is 8. So that's going to be my A, right? Just 8. So now that I know this is a geometric sequence, I have my A and my B. Now I can just fill that in, right? So I'm going to have 8 multiplied by 1.05 raised to the n minus 1 power. Right? And that's just the formula that we use, just plugging in those two numbers. So that's our answer for this one right here, for our nth term, right? So now we can do the same thing, but with what, Google Plus users, right? So I'm still going to have 6 months that I'm tracking. So 1, 2, 3, 4, 5, 6. Right? And then I can fill in the column by the first month to the 6th month. So we start at 3.8. And then we go to 3.68, 3.56, and so on, right? So we're just filling in this row of numbers with our column. So we go to 3.44, 3.32, 3.2, and that's our last one, right? So I'm going to do a similar thing that I did over here, but first I have to decide if it's arithmetic or geometric, right? So is this arithmetic or geometric with how we're changing? So what do we think? Is this arithmetic or geometric?
Arithmetic.
Right, so it's arithmetic, and what are we changing by each time? So what are we adding or subtracting each time?
0.12 subtraction.
Yeah, so we're negative 0.12, right? So we're subtracting 0.12 million each month that we go on, right? Okay, so we have that, and now what is our first term? So what is our A in this case?
3.8.
Yep, 3.8. Okay, so now we can just plug that into our arithmetic formula, right? So we have 3.8 minus 0.12 multiplied by n minus 1, right? And that should be our arithmetic sequence, right? So A, in this case, it's a geometric sequence. It's also an example of exponential change. So I'm just going to write exponential up there. And then this one is arithmetic, or it's also linear change. So it's just two words for the same concept. Exponential change, linear change is the same thing as geometric and arithmetic. Okay. All right, any questions on this first page?
Just to clarify,
Mhm.
because I feel like I'm following along and I'm getting it, but
Mhm.
so with exponential,
Mhm.
we're raising b into the for n minus 1.
Right, because we
Right.
started on the first term, right? We
Right.
started on the first month. Yep.
But then on when we're doing arithmetic or linear equations,
Mhm.
we're multiplying the
Mhm.
for b,
Yeah.
correct?
Yep.
Okay.
Yeah, so and the reason that is this one, if you're raising something to some power, it's repeated multiplication. So I'm multiplying 1.05 by however many I have, right? Whereas arithmetic, I'm just subtracting 0.12 to n minus 1, right? So multiplication is just repeated addition or subtraction, right? So that's why we call this one arithmetic, because we're just adding or subtracting each time. And geometric just means that you're multiplying by something each time. Okay?
Perfect. Thank you.
Yeah, any other questions on this page? Okay. All right, so we'll go on to the next page then. A little bit of terminology here. So it says a function is a rule that assigns a value of an independent variable known as the input, and then you get exactly one value of the dependent variable known as the output, or the function value. If a relationship pairs an input with more than one output, then the relationship is not a function. So we'll talk about this a little bit more at the end of the semester. So just know that a function, basically what it is it's just one of the sequences that we talked about, but we have an equals sign now. Okay? So an example that they give is they have this value here. So it says however many weeks or number of hours you worked is how much you're getting paid in a weekly salary. And basically what they're doing is they're saying that your salary is determined by 1575 times n, times the number of hours you worked, right? So the way we can say is this 1575 is basically just their hourly wage, right? Multiplied by however many hours that they work. Okay? And it looks like they drew it on the graph as well, right? So they just plotted these points in this column here. So they plotted a point at $15,236, right? And they plotted this on the graph right below. So I'm going to connect those dots really quick. And notice how we make a straight line in between all those dots. So if I had to take a guess, is this sequence or this function here, is it linear or exponential? So in the example that they give, is this function, or is this table here that they use to get this function, is it linear or exponential?
Exponential.
Is it exponential? So if we look at the graph, do you see an exponential change or do you see a line?
Okay. Oh,
right.
Right.
So that's how we're going to start relating our linear and exponential change to graphs. If you have a straight line on a graph, that's going to show linear change. Okay. So if you see a straight line when you graph something, that's a linear change. And if you have a graph that's going to do something, maybe something like this, where it kind of starts curving, that's going to be your exponential change. Or your geometric sequence, either one. Okay. So a lot of the times, maybe for your job or, maybe sometimes it's just in this class, I don't know. But it says we will often be presented with a situation or problem we want to understand better. So to do this, to understand that problem better, we determine the variables involved and their relationship to each other in a process known as modeling. So basically what this example is showing is that going from a chart to some function and then graphing that, all this is known as modeling. So it's just this process to help us understand what's going on with this column right here. Okay? All right, so we'll go on to the next page. So we have an example here. It says, suppose the owner of a new company has a goal of gaining 500 new customers each quarter. So it says, write a function to model the relationship between the number of fiscal quarters and the total number of customers. Okay. So what we're going to do is we're going to create a sequence again, right? But the way we're going to do that is we're going to look at the chart, and we're also going to kind of look at the graph just to see what's going on. So if I look at the graph, I can tell right away what type of sequence it is, right? So is it linear or is it exponential?
Linear.
Linear again, right? We have a line. So it's a linear change. So since it's linear, I'm going to have my sequence in the form of a times b to the n minus 1, right? So something like that form. Okay. So what is my a in this case? So I'm just looking at the total number of customers, right? What's my a in this case? Oh,
0.
sorry. That should be a plus, right? Not a multiply. Apologize for that. Yeah, so my a is 0. What is my b in this case? So what am I? Yeah, my b is 500, right? Okay, so if I plug those two into this formula, we get 0 plus 500 multiplied by n minus 1, right? So if I put in the 0th quarter, so if I put in 0 for n, we get 0 minus 1, which is negative 1. Negative 1 multiplied by 500, we get negative 500, right? So that's a problem. So where do we mess up? Right, so if we plug in 0, we're going to get negative 500. But if we plug in 0, we should get out 0. Right, so where do we mess up on this change or this equation right here, this function?
Do we have started with 500?
Start with 500 for here.
Mm-hmm.
Right, so
No.
we could. Yeah, so we have two different options, right? So we could either start with 500 as our first term, and this would be correct, Or we could say that our starting term, or maybe this n over here needs to be changed, right? So how could I change this part right here so I get 0 when I plug in 0?
+1 instead of -1.
Right. So what we're doing is, since we started on our 0th term, we just need to add 1 to this right here. So our correct sequence should actually be 0 plus 500 multiplied by n, right? So we're just adding 1 term to the sequence because we're starting on the 0th term rather than the first term. Okay. So if I wanted to simplify this even more, 0 plus anything is just that, whatever that is, right? So that's just 500. And 500 times n is just 500n. Okay. So my function, so I'm just going to say t for total customers is going to equal 500n. Okay. So we have our equation, right? So we have this function right here that'll let us know whatever nth quarter it is, we can find out how many customers he has, right? So my next question is, and see how they have this down here as well. So we have the nth quarter, we have how many customers we have. Okay. So if I wanted to know, it says use the table graph or equation to determine how many customers the company would expect to have after 5 years, and also how long it'll take to find 100,000 or to reach 100,000 total customers. Okay. So if I went 5 years into the future, what would I have to plug in for n for just the number of quarters, right? So how many quarters are there in a year? 4, right? 4 quarters in a year. Yep. So if I multiply 4 quarters by 5 years, we should get 20 quarters, right? So to find out how many customers they'll have after 5 years, it should just be t equals 500 multiplied by 20, right? The 20 quarters is how many quarters there are in 5 years. So if I multiply those together, we get, what, 10,000 customers? So assuming that he keeps growing at the same rate, he gets 500 customers every quarter, he'll have 10,000 customers at the end of 5 years, right? So can anybody make a guess on how many quarters it will take to get 100,000 total customers? So what can I do to find out how many quarters it will take to find 100,000 customers? Does anybody have a guess maybe? So I know that I'm going to use the same formula again. So it's going to take 10 quarters to find 100,000 customers.
No, 20 10.
Yeah, so I think 10 is a little low, right? Because it's going to take us 20 quarters to get 10,000 customers, right? So if it's less than 20, we're going to have even less customers than 10,000, right? Well, if I know that it takes 5 years or 20 quarters to get 10,000, right? What if I multiply this by, what, 10? So 100 or 10,000 multiplied by 10 is our 100,000, right? So if I multiply 20 quarters by 10, I get 200 quarters, right? So if I use 200 quarters, so what if I plug 200 in for n? Well, what's 500 multiplied by 200? Well, I'm getting 100,000, right?
Right.
So we're just multiplying this part right here by 10, right, on both sides. So what if I didn't want to do that? What if I wanted an easier way? Well, t, this is just the total number of customers. I know that I'm going to have 100,000 customers, right? So 100,000. And I know that's equal to 500 times n, right? Because we don't know how many quarters it takes. Well, one special thing that we can do, and you'll see this a little bit later, but we can solve for n now. So we're trying to get n by itself. And the way that we can do that is we can do the opposite or the inverse operation. So instead of multiplying by 500 on both sides, we can just divide both sides by 500. So I can divide the right side by 500 and the left side by 500. Right? So we have 500 divided by 500 on the right, so those will cancel. And what is 100,000 divided by 500?
200.
200, right? So there's another way that we could solve for it, right? Without having to like guess and check like we did the first time. So maybe that'll come in handy on some of the questions that we'll have on the homework. So you don't have to guess and check. It'll just be an easier way to solve it. Okay, so any questions on that one, using the table to find some answers? Okay. Okay, so we have a few terms that we're going to go over. So if we're talking about a linear function, we have two different types of linear functions, or two different ways that they can go. If we have function values that are increasing, we call that linear growth. So in our case up here, this is linear growth where we're going up. Okay? And if it's going down instead, we call that linear decay. So I'm going to draw a few charts down here at the bottom. So I'm going to label this A. So this is linear growth, and it's going to go up like that. So we're going up and to the right. And if it's linear decay, we're going down and to the right. Okay? So if you put a ball at the very start, it's just going to stay there. But if you put one up here, it's going to roll downwards, right? So that's the difference between linear growth and decay, if you look at a chart. Okay. And then we also have the same thing, but we have it for exponential growth, right? I think that's on the next page. No, it's not. Okay, so I'll just label that here. So if we have exponential change, if we have exponential growth, so I'm going to label that C, exponential growth, it's going to look something like this, where it's still going up like linear growth, but it's going to go more of a curved line, and it goes faster and faster as we go up. Okay? And then with exponential decay, so I'm going to label that D, so exponential decay, we're going to start up pretty high, and then we're going to come down really fast, and then still going down, but we kind of start to level out at the end. So that's our exponential decay. Okay, so any questions about what these four terms are or what they represent? Okay, all right, so we'll go on to the next page then. So the next one says, use the following data to determine if y is a linear function of x. If it is, explain why and write the linear function that models the data. So let's look at this one. Is this an example of linear, is a linear function? So is y a linear function of x? So is y changing by a certain amount each time, adding or subtracting, or not?
Yes.
Yeah, so what is it changing by each time?
6, positive 6.
Yeah, so we're adding 6
Adding.
each time, right? So every time we're just adding 6. Right, so my b here is 6. And what is my a? What's my first term? What's my first term here?
If we're going by y, correct?
Yeah,
First term is 18, negative 18.
right. So my a is negative 18, right? And notice how we're starting with 0, right, over here. So we're not starting with 1. So that's why I just put an x up here for you already. So it's not going to be x minus 1 because we're not starting on the first term, right? We're starting on the 0th term. So the way you can look at this is the functions that we had earlier. We had a plus b times by n minus 1. So in this case, instead of having n for our term number, we just have the letter x. So the way that we can fill this in is we just plug in negative 18 and then plus 6x. So the number that we're multiplying just always goes in front of the variable. And then our starting term is just by itself, right? We're just adding it together. Okay, so we have a linear function that models the data, right? So we can use that to find maybe the 10th term. So if I wanted to find the 10th term, so x equals 10, how can I do that with this that we just found here? So if I want to find the 10th term. So I don't know what y is, right? But I know that it equals negative 18 plus 6, and I want to find the 10th term. So what I'm going to do is just plug in 10 for x, right? So if I know that it's my 10th term, what is y going to equal? So what is my value of my y at my 10th term?
42.
Right, and how did you find that?
Well, I added 60 to negative 18 or subtracted 18 from 60.
Yep, so we just have negative 18 plus 60, we get 42, right? And that makes sense in the context of our table, right? Because we keep getting bigger and bigger positive numbers over here. So you'd expect as we get farther and farther into this term or this sequence, we get larger and larger numbers as we go down. Okay. Okay. Any questions on this one? Okay. So now let's get a little bit more abstract. So this one says you have an interest-free loan of $800 and you're paying it off at $50 per month. So it says model the situation with a table, graph, or equation. So I'm just going to do a rough graph. So I'm going to start with a rough graph up here. So my y-axis is going to be the amount of money that I have on my loan. Let's say the amount of money I have on my loan. And then my x-axis is just going to be the number of months that I've been paying it for. So they're just the number of months, okay? So I'm going to start with $800 that I owe, right? I'm going to start with $800. And I know that I'm paying it off at $50 per month, right? So I know that it's 800. If I look at 750, so if I go to 750, that's going to be my first month, right? Because after I paid $50, I should have 750 left, right? So I'm going to kind of create this line, and it keeps going down and down and down, right? Because I'm paying it $50 a month, right? So I want to know what my A and my B are, right? My A and my B. So can anybody tell me or make a guess as to what my A is? So what's my starting value?
800.
Right? Because I'm starting with a loan of $800, right? So what is my B? What am I changing by each time?
$50
Right. So is it a positive or a negative $50?
minus $50.
Right, because we're subtracting $50 off that loan, right? We're taking away $50. Yeah. So is A, is that going to be my 0th term or my first term or my second term or so on? So what term is A? I know it's my starting term, but is it my 0th or my first or my second or so on?
Here's the first term.
So we have to be careful, right? So when I first take out this loan, it's going to be my 0th month, right? So if I look at kind of the graph that I made, it's our 0th month, right? Because we haven't made any payments yet. So A, I know that this is my 0th term. And that's important when we make our sequence, right? So I know that I had A, which is going to be 800, and then minus 50, right? And I'm just going to multiply that by M. And M is just the number of months that I've been paying on it, right? So if we've been paying on it for 2 months, we subtract $100 and so on, right? And I'm just going to label this. So I'm going to say this is equal to, and I'm just going to label it with a big L, and that's just how much money we owe on that loan still. Okay. So is this function linear? Is it linear or is it exponential?
It's linear.
It's linear, right? Because we're just subtracting by a certain amount each time. So it's linear. So how many months will it take me to repay this loan? So how many times do I have to pay $50 to get to $800? So how many $50 increments do I need to pay to get to $800?
16
16, right? So how did you find that out?
divided 50 on each side.
Yeah, so if I do 800 divided by 50, we get 16, right? So it's going to take us 16 months to pay back that $800. Right? So you just need 16 months of $50 increments to get up to that 800. Okay. Okay, any questions on this page? Okay. All right. So we'll go on to the next page then. So the next page, we have another example, but it's going to be a little bit different, right? So this one says a virus is contracted by 100 people, each of whom infects 2 more people the first day after which they're no longer contagious. So it says write a function to model the number of new people sick per day by the virus. Assume that the infection will continue to spread from each sick person to 2 additional people. Okay. So on day 0, how many people are infected with this virus? So on day 0.
100.
100 people, right? Because that was just in the problem. So we start with 100 people, and each person infects 2 new people, right? So how many people do we have infected on day 2?
200.
200, right? And then how many on day 2?
4.
400, right? So we're just multiplying by 2 each time. So for day 1, if I want to fill in this chart down here, we start with, well, day 0, I guess, is 100, right? So day 1 is 200 people. And then we get 400 people, 800, 1600, 3200, 6400. And then we have what? 1,280 people? Yeah. Right. So we can kind of see, that's what's modeled on this graph, is we start out with not a lot of people, right? But then as the days go on, because it's exponential, it starts growing in this pattern right here, this exponential growth, right? So it just kind of goes up. So I want to write a function to model this, right? So I want to know what my first term is, so what's my A, and what am I changing by each time, what's my B? So what is my A in this case?
100.
Sure. So let's start on day 0, and let's say it's 100 people. Okay. So I have A is 100, and what is B?
2.
2, right? It's just what I am changing by each time. I'm multiplying by 2. Okay. So I can say I, the amount of new people infected. So I'm just going to choose I, but it doesn't really matter what you choose. So I is just the number of new people that were infected. That's equal to, so 100, which is our starting term, multiplied by, we're doing 2, right? Because we're multiplying by our change 2, raised to the d. I'm going to write d, lowercase d, just for the number of days that have passed. Okay? So that should be my formula for how I can find out how many people on the nth day. Okay. All right. Any questions on that page?
Yes, I have a question.
Mm-hmm. Yep.
How, on the actual, not graph, but the fill-in part,
Yeah, the table.
yeah.
Mhm.
After the 6 is the N, it says N. How did you get
Oh.
N is 12,800?
Yeah, so that was wrong. I just thought that was the 7th day. Sorry about that. So the nth day is just this formula that we found down here, right? So we don't know how many
Okay.
days we have, but it's the nth day, right? So this actually should be 100 multiplied by 2 to the nth power, right? So instead of substituting in some day number, we're just going to substitute in the letter n. So how many days it's been n days.
Okay, thank you.
Yep. Any other questions? Okay. All right. So I forgot that it was later in the thing, but the exponential functions, we have two different kinds. We have an exponential growth and decay. So I've already covered that, so I'll skip that for now. But one special thing that we have is we have something called a multiplier. So a multiplier, all that is just your b. So b is your multiplier in exponential change. So it's just whatever you're multiplying that first term or your starting term by. All right, so if we have this example down here, it says a company wants to project growth using both linear and exponential change to see long-term effects. So it says the company begins with 150 clients. So that's our A is 150 clients, right? And they want to project growth assuming that there's 15 new clients per month versus a 10% growth rate for clients each month, right? So my B for my B for linear growth is 15. And what is it for exponential growth? So what's my multiplier if I want to try the exponential growth? So we have a 10% increase, right, or a 10% growth. So what is 10% as a multiplier if I'm increasing? So that's changing a percent increase to a multiplier, right? What we did a few sections ago.
0.01 times multiplied by 0.01.
So 0.01 would be 1%, right? So if I do, so
0.1.
Yeah, so if I look at 0.1, if I multiply, let's say, $100, and I multiply that by 0.1, I get 10, right? But I want to look at an increase of 10%, right? Because this is just telling me what 10% of something is. So remember when we went back to multipliers, instead of 0.1, we need 1.1, right? So we need 1.1, and that gives us 110, right? That gives us that growth of 10%. So our multiplier here is 1.1. So that's a 10% growth. I know some people might have done that and then like added the $100 back in, which is just the same thing as multiplying by 1.1. Okay, so what would my function look like for my linear growth? So I'm going to say for customers, for my linear growth, what would that look like? So what should that formula be for my linear growth?
150
Yep.
plus 15 times 1.1.
So times 15, I agree up to that point. But we want to know, these are going to be two different formulas, right? So this one's going to be for linear, and this one's going to be for exponential.
Oh, okay.
Yep. Yeah, so I agree up to that point. So we have 150 plus 15, and we're assuming that we get 15 new clients per month, right? So it just depends on how many months have passed. So I'm going to just label that M. So our growth of our clients is just 15, or 150 rather, sorry, plus 15 times however many months have passed. Okay. Yep. And then we can do the same thing for exponential, right? So the number of customers for an exponential, well, we start with 150, right? And we're going to multiply that by 1.1, which is our B. And we're going to raise that to the M power, right? For how many months have passed. So how can I find, it says how many months will it take for the company to reach 500 clients with each approach? So the first one, how can we find how many months it's going to take to reach 500 clients? Does anybody have any ideas?
Divide 500 by 15.
Yeah, so if we did that, we would assume that we started with 0 clients, right? But we started with 150.
Mm.
So what I can do is, what if I do 500, so how many clients I need, and what if I subtract that by 150, right? So actually I only need 350 clients. And then I can divide that by 15, and we get about 2.3 months, right? So what I'm going to say is it takes about 23.3 months to get those final 350 that I need, right? And then I can do something similar with the next one. So I don't think the homework's going to ask you to actually solve something like this. I think what they would be more likely to ask you is how many clients do they have after 10 months, right? So if I give you how many clients they'll have after 10 months, you just plug in 10 for both the M's. Okay? So I'm not super worried about that. But if it takes 23.3 months to get here, what if we plug in that 23.3 and plug that in for M over here? So after 23.3 months, how many clients will I have with the second method? So if I do 150 multiplied by 1.1 to the 23.3 power, and maybe this will be a lesson on the calculator if some people haven't done this. So if I have 150 and I multiply that by 1.1, there should be a thing in the math over here. So math, and you can raise that to, I'm just going to write to the third power. Okay, and then what you can do is you can just press the left button and it'll kind of shift up here, and I can just write 23.3. Right? And press enter, and we get 1,382 clients, right? So if I plug that into my calculator, it's 1,382. I'm just going to round it off to the nearest client. And we can tell that that number is way bigger than the 500 clients that we found up here, right? So I know that it's going to take less than that amount of time to reach the 500 clients with this growth, right? So I know that the exponential change is going to be better, or you'll get 500 customers faster than the linear way.
Doing something wrong.
So another way you can do this on your calculator, if I have 150 multiplied by 1.1, if anybody sees this little caret button over here, I just call it a caret button. It's right under my clear button, but you press that, and then you can raise it to the 23.3 power. That's another way to do it. Okay. All right. So does anyone have any questions on this problem? Okay. We will go on to the next one then. Okay, so this one says, city planners for a city with a current population of 100,000 residents are modeling the population in various ways to help them make decisions related to resources. So it says experts disagree on the growth rate and model since they're using different data, but we do know that they have resources for only 200,000 residents. So it says for each scenario, write a function and use it to determine when the city will be its maximum capacity. So I am not going to worry about the second part there, but I do want to write a function for A, B, C, and D. Okay. So the first thing that we need to do whenever we're writing a function is we need to determine, is it a linear or exponential function, right? So if I look at the first one, the population increases by 5,000 residents per year. Is that linear or exponential change? So what do we think? Is it linear or exponential?
Maybe linear,
Linear, right? And why is it linear?
because it's a consistent number.
Yep,
That
you're just
you-
adding a consistent number, right? Yep. So this one's linear. What about B? Is that linear or is it exponential?
Still linear.
Linear, right? What about the next one? What about C? Is it linear or exponential?
Exponential.
Exponential, right? So this one's exponential. And the last one is also exponential, right? Because we're increasing by 3%. Okay. Okay, so we've determined if they're linear or exponential, right? So now we can make the function. So for A, so what can we do for A? Well, we can say that they have the number of residents, so capital R, is equal to,
I know, but is it
we
like
can say,
what in your
sorry about that. So we can say that the number of residents, so however many we have in the city, is equal to, and what is it equal to? Well, we need to know what our A and our B is, right? So what is our A in this case? So how many residents do we start with? So how many residents do we start with?
100,000?
100,000, right? So we start with 100,000, right? And then I know it's linear, so I'm going to add. And what am I changing by each year?
5,000.
5,000, yep. So I'm changing by 5,000. And what letter or what variable do we want to use to represent the residents that we change by per year?
Doesn't matter. Can we stay consistent to like N so that we're
So the
Does that
reason
make-
that we don't use consistent variables or use the same variable every time is because we like to have the variables give a little bit of meaning to the problem, right? So R in this case is just the number of residents in this town, right? So 5,000, maybe we should multiply that by Y, because that's just how many years have passed multiplied by the 5,000 residents, right? So you can use any variable and it's correct. But maybe the preferred way to go is by using variables that would represent certain things in the problem. So it's kind of like a reminder for us, if that makes sense.
Yeah.
Okay. So how would this equation that we have change with part B? So the number of residents that we have.
You would just change out the 5,000 for 8,500.
Right. So it's going to be the exact same thing, except 5,000 is going to be 8,500 now. Okay. So it's just the exact same thing. We just switch out those two numbers. Okay. So can we use that same trick for part C?
No,
Right. And why can't we use the same trick?
because we have to use a multiplier because it's a percentage.
Right. So we have an exponential here, but we have a linear here, right? So they're not the same type of problem, right? So I can still start with R, right, which is the number of residents, and that's going to equal to, my A is still 100,000, right? But then I'm going to multiply that by what? What's my B in this case?
A.
So what's my B in this case? So I know that I'm increasing by 2.5%. So what is 2.5% as a multiplier?
Oh,
So I know that it's an increase, right? So all we need to do is just change that to a decimal and then add 1. So my B here should be 1.025. Okay. So that's from our multiplier section. It's just 1.025, right? So I'm going to plug 1.025 in, and then I'm going to raise that to the y power, right? Because that's just how many years has passed is what we should multiply that growth by, or raise that growth to that power. So we can use the same equation again for part D, right? So we can do the exact same thing, but we're going to change what the multiplier is. So we have R equals 100,000 multiplied by, and what's my B in this case?
1.003.
Just be 0.3, right?
Right,
Just 1
sorry.
0. Yep. Yeah, so we have 1.03 raised to the y power. Right? And then that's our equation for that.